Okay, so welcome to the second part. So so first part was the set theory, and in the second part, I want to talk about some tools from infinite combinatorics. Just to wrap up, I mean, for the first part, I mean, Elena told me that she feels now insecure in whatever you prove. So I mean, that you have to realize the situation is really bad because ZFC, if ZFC is our framework for what can be mathematically proved, so we cannot prove that it is consistent. So we do not know that the mathematics that we work in is consistent. So this doesn't bother usual mathematicians, but it really bothers logicians. So when I was a PhD student, there was a conference in which I had to review papers, and there were two papers that claimed contradictory statements. One says A and the other said not A. Now, in any other conference, you will say one of these must be wrong. But in a logic conference, you say, wow, maybe we found a contradiction in set theory. Maybe everything is provable. And yeah, so these two authors, one of them kind of politely withdrew his papers. And then maybe he has now in his pocket a proof of inconsistency. And you know that if you have a proof of inconsistency, you can use it to prove everything now. So you just have to use it sparingly so nobody will suspect that you have the inconsistency in your pocket. Okay, so in this part, I want to talk about some infinite combinatorics tools. I don't know how much of this will manage to cover because but it's kind of really enjoyable, and we had some results in machine learning based on those tools. So the first tool that I want to talk about is cofinality. So what is cofinality? So we are back in the world of orderings, but now I don't require my orderings to be well ordering. I'm just talking about any ordering. So if you have an ordered set X, a subset is said cofinal in X if for every element of X, you have an element of A above it. So you see, so if I have here an ordering, so if this is my set X, and my set A is these elements, so this is A, I say that A is cofinal if for every X in X, I have some element of A above it. And the cofinality of an ordered set X is the minimum size of an A which is cofinal in X. So you ask how, I mean, you have the ordering X, and you go to home hardware, and you want to buy a ladder, and you want to ask, how big should the ladder be so that I will be able to climb to the top of X? And the point is that you can start anywhere. So it follows that if you have if X has a maximal element, then the cofinality is 1. If it has the maximal element, this one element is cofinal in X. It is above any other element. So if X has a maximal element, it's boring, the cofinality is 1. In particular, every finite set has cofinality 1. So it's very different than the cardinality of the set. And it has to do with the ordering. So what about the real numbers? I mean, the natural numbers, the cofinality of the natural numbers is, of course, it's not 1. So the cofinality of the natural numbers is going to be Aleph 0. Because in order to reach the top of the natural numbers, you need an infinite set, countable. But the same is the cofinality of the real numbers, because the set of natural numbers is cofinal in the reals. So if you just have the countable set of natural numbers, it is a set of size Aleph 0, which is cofinal in the reals. So we feel like we can reach very big sets with countable cofinality. Or if we look, for example, at this huge set Aleph omega with some well ordering, it will have cofinality omega, countable cofinality, because you will just make steps at every aleph n. So cofinality is very different than the cardinality. So you can ask, so here I have all kind of examples where the cofinality is aleph null, and you can ask, are there any sets that maybe every set has cofinality aleph null? So it turns out that, of course, it would have been very boring if that was the case. And so we have this example. So I look at all functions from the natural numbers to the natural numbers, and I order them by eventual dominance. So we can draw this picture. We said we have functions from the natural numbers to the natural numbers. So here I have the natural numbers, and here I have the natural numbers, and I have a function, some f, and I have some g, I have some other function g, and f is above g if from some point on, everywhere above it, f dominates g. So we say that f is below g if there is some m0, some point here that g crosses f, and from that point on, g is above f. So of course, it's just a partial ordering. I can have two functions that keep crisscrossing each other, and none of them dominates the other. It's a partial ordering. We can still ask about the cofinality of a partial ordering. What is the minimal set such that nobody is above an element of the set? So for partial ordering, I said the set is cofinal if no element of X is above the element of A. But so what I'm claiming is that the cofinality of this partial ordering after the countable, after the eventual dominance, that the cofinality is uncountable. So here we found the set and ordering with uncountable cofinality. And what is the proof? The proof is usual diagonalization argument. So, okay, so I want to show you that you cannot have a countable sequence here that will be above everything. So you give me a countable sequence of function, and I want to show you that I can have someone that dominates all of them. So how will I do it? I will define a function u function g. And g of n will be the maximum of all the fk of L such that k on L on n less than n. So you see, I take here maximum only over finitely many functions. And for these finitely many functions, I just look at the finite initial segment. So here I have a collection, a finite collection of numbers. So I can define g of n to be above it, to be this maximum plus 1. So what will happen is that this g dominates each of my functions, because you see, if I have here my countable collection, say f1, and I have f2, and I have f3, and so on. G that just says, okay, at the beginning, I need to go above f1. At this point, I have to go about f1 and f2. At this point, I have to go about f1 and f2 and f3. So my G will be above all of them in eventual dominance. So no countable subset of this collection of functions is cofinal. So we have a set of uncountable cofinality. Okay, so the cofinality is not trivial. I think we can have sets of uncountable cofinality. And now the question is, how is it related to machine learning? And so that's a paper that I had with Tosca in Colt 2024, that we use this idea of cofinality to show that there can be no dimension that characterizes learnability of classes of probability distribution. So let me just stop for a second and explain what the problem is. So we know how to characterize learnability of 0-1 predictors. But now I want to learn a collection of, so I have here Q is a collection of probability distributions, and what is my problem? You pick from unknown distribution P in this Q. You give me a sample S, which is IID picked from P, and I need an algorithm A of S that will give me some element in the realizable case. I want A of S to be a member of Q that will be as close as possible. That's a probability distribution that will be as close as possible to the P that generates the sample. So it's a very basic question. I mean, you have a sample from a distribution. You want to know what the distribution is. That I think we agree that it's a very basic question. And of course, if we don't restrict Q, then we cannot do it. So that's my famous lottery example, right? And I think most of you heard of it or noticed it. I mean, the lottery example is that you have a lottery, and every week you throw 10 dice, and if you had the outcome, then you win the lottery. So I'm the lottery operator, and I want to cheat. So I throw the dice 1,000 times, and I record all of those results. And next time when I have to publish my weekly lottery, I just pick from this collection of, I buy 1,000 tickets. I mark them with the 1,000 results that I already have in my pocket. And now next week, I will just sample from this 1,000. And each time I will win the lottery. And now if you are a regulator and you watch the results, will you be able to detect that I'm cheating? And the point is that there is no way, because if I randomly sample from this 1,000, as long as I don't have repetitions, it looks like I was sampling from the original distribution. So what I'm saying is that there are collections of distributions. So say this, all subsets of the uniform distribution over so many draws that are very difficult or impossible to learn. So we ask which families of distributions can be learned. We know, for example, that mixture of Gaussians can be learned. We have this nice paper with Hassan that gave a sample complexity bound if your family Q is all K mixtures of Gaussians in dimension D. So we know that those sets can be learned. And we know that there is some sufficient criteria for learnability of probability distribution. So that's a very basic problem if you want to do statistical learning. It was open, we have records of it open from 1994, and we have even papers, recent papers that saying we make no progress on this problem. And the question of how do we characterize which families are learnable, and in this paper with Tosca, we show that there can be no characterization. I mean, that's a typical kind of papers that I like to be co-authors with, that show that something is completely wrong, or there's no dimension, or there's independent, or something very non-constructive. Okay, so how did we do it? So the trick here is to say that what does we have? Of course, in order to show that there is no dimension, I have to tell you what a dimension is. And as a model, we look at the VC dimension. So a dimension is something that I give you a family of probability distributions, and you want to look at the learning rate. So what is, if you want to approximate up to epsilon with probability greater than 1 minus delta, you want to find which element of Q generated the sample. You want to have a learning rate. And a dimension is something that tells you that if you knew the dimension, now the learning rate just depends on epsilon and delta. So a dimension is a characterization of the family, such that if you know this, tells you how complex the family is. Now the sample complexity is just a function of epsilon delta. You can see it in the VC dimension, because we know that for learning binary functions, binary valued functions, we know that this function is just something like, how many samples I need for epsilon delta, I need something like VC dimension of H plus log 1 over delta divided by epsilon square. So you can see that this is a function. Once I know the VC dimension, it's just a function of epsilon delta. Yes? Oh, wait, that's a typo. Good question. What I meant, I didn't mean it's multiplicative. Even you can see it directly in this example. What I meant is that the MQ of epsilon delta is just a function of D of Q, epsilon, and delta. The main thing is that all I need to know about the family Q is its dimension. I don't need any other information. And we know that's exactly the case with learning binary labeled functions. If you know the dimension, you don't have to ask yourself anything else about the class. Okay, so that's, okay, so there is a typo here. This should be F here of D and Q and epsilon delta. All you need to know, in other words, D of Q is the only information required to determine the sample complexity of the class Q. Yes? What? We show that there is no dimension that gives an upper bound, but of course, if there's no dimension that gives an upper bound, there is no dimension that gives you the exact bound. Okay, okay. So we cannot, by the Tosca, we want to show that we cannot get this. Yeah. Okay. So how do we show it? How does it connect to cofinality? So the trick is that to notice that we can view those learning rates as functions from the natural numbers to the natural numbers. So if I have some learning rate, I can put epsilon to be 1 over n and fix delta to, delta is not playing a big role here. So let's fix delta to 0.1. And now those learning rates are functions from natural numbers to natural numbers. So I'm just looking at this learning rate, MQ. I'm looking at MQ of 1 over n and delta equals 1 as a function that goes from the natural numbers. This is my input natural numbers to the natural numbers, which is how many samples will I need. So I can view those as functions from the natural numbers to natural numbers. So I get here a collection of functions in my space of n to the n that I talked about. And now the observation is that, right, so even before we see the proof, the observation is that if you have a dimension, then this collection, it's a subset of n to the n, has countable cofinality. So we have this big set. You see, so we have this big set, which is all the functions. We have this big sets, which is all the functions from n to the n. And we have the smaller sets of all the functions that can be written as mq of 1 over n 0.1 for any q. Those functions will have countable cofinality if I had a dimension. Why is this the case? Because if I have a dimension, then those functions, they all look like, again, I have the same typo here. They all look like a function of the dimension and n. So every such m of some q of epsilon delta of 1 over n delta equals 0.1, every such will be a function of d of q and 1 over n. And that input, d of q is a natural number, n is a natural number, so I have here only countably many possible inputs. So if I had a dimension that characterizes, that upper bounds this learnability, then this collection will be a countable cofinal set. So the conclusion is that if we had a dimension in this very general way, just a dimension such that if you know the dimension, you can figure out the learning rate, then the set of all learning rates will have countable cofinality. And now this gives us a tool to show that there is no such dimension. So now all we need to show in order to show that there is no such dimension is that this set, for if my families are classes of probability distributions, this set cannot have countable cofinality. So how will I tell you that this, how will we show that this set does not have countable cofinality? So we want to show that the set of all these MQ, such a Q is the class of distribution under the partial dominance, the ordering is uncountable cofinality. The cofinality is uncountable. So how are we going to show it? We already know of one set that has uncountable cofinality with n to the n. So I will show that this set, the set of all functions of this one, is cofinal in n to the n. And since n to the n has uncountable cofinality, if this set is cofinal in it, it also has right, because it also must have uncountable cofinality, because cofinality is transitive. So you see, if I could take the natural numbers and embed them cofinally in all the sets of learning rates of some m q of some 1 over n 0.1, and then I will take this set, and I show you now that this set is cofinal in n to the n. Then you will take every natural number, put it here, transform it to here. If the natural number, if this is have countable cofinality, I will get that this guy has countable cofinality, which is a contradiction. So now to finish our proof, we just have to show you that this set is cofinal in n to the n. And then we know that there is no dimension. Okay, does it make sense? Yeah. So we just want to show that this does not have countable cofinality. It's enough to show that for every function from n to the n, I can find a class that dominates this function. So my set of all learning rates is cofinal in n to the n. Therefore, it has uncountable cofinality. Therefore, you cannot have a dimension. So I will not go into this part too much. I'll just give you a intuition of what is the construction here. And because I don't want to go too much into the machine learning, I care more about the tools, and here the tool is cofinality. So what is the trick? So the idea here, even before I get into this, it goes back. I think that most of you are familiar with the fat shattering dimension. The fat shattering dimension is trying to tell you, it's trying to describe how difficult it is to learn a function in the, I want to learn a function in the L infinity norm. So I have here an unknown function, and you get points, and you get the levels here, and you want to learn the function. And the question is how many samples you need. And now it turns out that you have two parameters playing here. One parameter is what do you mean to approximate the function? So if I want to just approximate the function to within epsilon, that's one parameter that I can ask. How well do I want to approximate my unknown function? And the other parameter I can play with is once I'm within this epsilon, how complicated is my class here? And these two are independent. I can say for every epsilon, I will find a class that is very complicated at this level, but not so complicated in other levels. So I can play with these two parameters, the level that I'm aiming for and how complex it is in this level. And I can do the same, we can do the same with learning distributions. So we are learning distributions in total variation. And we have two parameters to play with. One of them is that from which approximation level it becomes difficult. And once you're in approximation level where it becomes difficult, I can independently ask how difficult it is going to be to learn at this level. So the point is that if I want to control the level of complexity of learning a class of functions, I can have functions that, say I'm looking at functions over the natural numbers, at distributions over the natural numbers. So I take a point here, and I say all my distributions have weight 1 minus epsilon on this point. So in order to learn my distribution up to precision epsilon, it's very easy. You just give me the distribution that sits here. And now for the rest, I can make it as complex as I wish. I can take here a big set and play the lottery game and say I have here this some set of some big size. I don't know how I denoted it here. Some big size k, doesn't matter. And here my class will have all possible uniform distributions over a subset of here. So if I want to learn up just to approximation epsilon, very easy. If I want to go further than approximation epsilon, then I'm running into having to decide was there a cheating in the lottery or not, which is very difficult. So I have this control of these two parameters at which epsilon things kick in and when they kick in, completely independent of epsilon, how difficult it's going to be. So by playing with these two parameters, we can have classes Q and K such that if you want to learn them to approximation 1 over n, you need k many samples. And since I can play with these two independently, I can now start with any function in this n to the n and look at this class that says that for approximation 1 over n, I will need f of n many samples. So my complexity of this class will dominate f for every f, because we can play with these two parameters. So what we showed is that the class of learning rates of probability distributions is cofinal in n to the n. Therefore, it does not have a countable cofinality. Therefore, you cannot have a dimension that will bound upper bound every learning rate. Yeah. No, I cannot show. It is a very good point. I don't know. I mean, I read a good point in your question. I'm not sure that's what you asked. This construction does not show you that you cannot have a scale-sensitive dimension.
So in this argument, you were treating d of q as a fixed quantity. But if
right.
q is a function of epsilon, you need only choose epsilon as 1 over n, and again, you have a function that's from the naturals, right? If d is also a function of epsilon.
If I allow d, but I can have for every epsilon, I can have a different function, which will be the sample complexity for that epsilon. Yes. And that could be a very high cofinality family.
But can't the whole thing m sub q be written just as a function of 1 over?
So let me just explain the question of Peter. The question is, there is a distinction between epsilon sensitive dimension and epsilon invariant, scale invariant dimension and scale sensitive dimension. Scale sensitive dimension says that you have rates that it is d of q and epsilon, and it tells you how complex it is to learn q to precision epsilon, right? And this, what we showed you, is just you cannot have just d of q. And I don't think it shows that you cannot have d of q epsilon.
So if there's an m q dq epsilon f of dq epsilon comma epsilon, then why can't you use the same trick of saying let's set epsilon to 1 over n?
Now you confused me. I know that you cannot. Tosca, you want to answer him? No, but yeah. Oh, okay. So anyway, so okay. So back to Peter is right, but this is a quantitative dimension that controls the learning rate. We can also ask about the dimension that tells you are you learnable or not. Just tell you learnable or not learnable. If the dimension is finite, you are learnable. The dimension is infinite, is non-learnable. We also prove that you cannot have a quantitative dimension for this, which does not work for scale sensitive dimension. But for the quantitative, you're right. Yeah. Okay. Yeah, good point. So yeah, because this was a 2024 paper in which we showed that you cannot have a scale invariant dimension that not only controls the learning rates, but also characterizes what's learnable and what's not. But at that point, we didn't know how to answer whether you have a scale sensitive dimension. And in a paper last year, in a paper in this conference, we resolved that problem and we showed that you cannot even characterize epsilon scale learnability. But that's not with cofinality. Yes. Right, very good point. What happens? So I ask you, what will happen if instead of natural number dimension, I will allow you a real number dimension? What will happen then? Right, right. So even the real numbers are also have countable cofinality. So sure, if your dimension is a function from n to the n, you overcome this, but that's not a useful dimension because you cannot even describe it. But real numbers will not help you because the real numbers also have countable cofinality. So even if I had a real number here, I will just have to make one more step from n to the real numbers, from the real numbers to my dimension, and it will still be countable. Okay, so that's how we used cofinality for showing that there is no dimension for learnability of classes of probability distributions. Yeah. Okay, so that was cofinality, and now I want to move to a new tool. Also was used this tool. We used it also in a paper with Tosca and Ruth. And this tool is a very nice tool, which is filters and ultrafilters. So what are filters and ultrafilters? So we forget about the orderings. And we want to define a notion. It has come from model theory. So we want to define a notion of majority. So if we have a finite set, we know what is a majority, if you are more than half of the participants. But if you want to have an infinite set, you want to define what is the majority over an infinite set. And that's what filters are trying to say. So F is a collection of majorities. Say you have an assembly, and in your assembly, you have all members of the set X, and you want to know, you have a vote, some set votes against, some subsets vote pro. You want to know who is the majority. So F is the collection of all the subsets that will count as majority. So what do we want from such a collection? In a very axiomatic, abstract way, of course, you want that if A was a majority and now more people are voting for it, then B will also be a majority. So a family of majorities need to be monotone in terms of set inclusion. You also, I mean, this is a strong requirement. You want that for every two majorities, the intersection is also a majority. So if everybody is voting for regulation 1 and everybody is voting, a majority voting for regulation 2, I have a majority for both regulations together. And of course, we want non-triviality. because otherwise I will say every subset is a majority. So you want to say that the empty set is not a majority. And this is called a filter. But of course, this will not solve the problem of voting. Say I have a voting over the countable numbers, over the natural numbers. All the odd numbers vote against, all the even number vote for. How do I decide? So for that, we have an extension which is called an ultrafilter. And an ultrafilter on top of it has the property that for every subset, either the subset is a majority or the complement is the majority. So I called it decisiveness, because if you have an ultrafilter, then whenever a set votes, you know it was the majority or the complement was the majority. So this is an ultrafilter. Yes. Right. So Mats asked a very natural question. How can we have this notion even of a finite set? And the answer is that we have it, and you have it in the US these days. And and this is what we call the dictatorship. That a majority, you have one dictator, and every set that contains the dictator is a majority. And if the dictator is not in the set, it's not a majority. So that's an ultrafilter. It's closed under intersections, and it says every set is either a majority or not a majority, just depending on whether this point is inside or outside. So here is some examples. The set of all infinite sets is it's not a filter? Yeah, it's not a filter. You can have two infinite sets, the positive, the negative, the odd numbers, the even numbers, you take the intersection, it's empty, it's not a filter. If you have a set of all cofinite sets, all the sets that is the complement is finite, then it is a filter. Because if you take intersection of two sets that each of them just misses finitely many points, the intersection will also miss only finitely many points. So it is a filter, but it's not an ultrafilter, because not every set, either it or the complement, misses just finitely many points. The evens and odds is a counterexample. It's not an ultrafilter. And this is now this dictatorship. For every point x, the collection of all A that's at x is a member of A is an ultrafilter. It's a dictatorship. Every set either is a majority or not a majority, according to which, if x is voting against or for this ruling. So that's called the principal ultrafilter, and it's not very interesting. Okay, so you have a notion of a filter, which is a collection of majority. And here are some more, these are majorities over the natural numbers. What about majorities over the unit interval? So for example, if I have the unit interval and I take the uniform distribution, then I can define a majority of all subsets that have measure 1. And notice that sets of measure 1, if I intersect two sets of measure 1, the intersection also has measure 1. So it is a filter, but it is not an ultrafilter, because you can have, the 0 to half, half to 1. None of them is measure 1, not the set, not the complement. Another example is the set of co-countable sets. If the complement is countable, you take the intersection, the complement will still be countable. So if you have an infinite set, the set of co-countable sets is also a filter. If you have an ordered set, so you say that this is a filter that will be used. The set of all subsets, now I'm back in ordering. The set of all subsets that it contains a final segment of X is a filter. Because you see, if I have here my ordered set X, and one set contains this guy, this final set, and some elements. And the other set also contains a final segment plus some elements. If I take the intersection, I will still have a final segment inside. So if I have a linear ordering and I look at all the sets that contain a final segment, then it is a filter. Okay, so it's another non-trivial filter based on the ordering. Anything unclear or question about this? Okay, so we can generate a lot of interesting filters. Measure one. You look like a question on your face. Okay. So we have this notion of a filter, but you can ask the natural question, do we have ultra filters which are not dictatorship? So far, our only example of ultra filter was a dictatorship. So that's the next question. And do we have non-trivial ultra filters? And the answer is that every filter can be extended to an ultra filter. And that should remind you of theorems like every independent set of vector space can be extended to a maximal independent set, that every two disjoint convex sets can be extended to this maximal disjoint convex sets, and so on. So indeed, this theorem is equivalent to all of those things. So set theoretic view, all of those are equivalent. The axiom of choice, Zorn's lemma that we discussed, every set can be well ordered, every filter can be extended to an ultra filter. For every vector space, every independent set of vector can be extended to a basis. All of them are equivalent. So since we accept the axiom of choice or Zorn's lemma as part of our mathematics, we also have this theorem that every filter can be extended to an ultra filter. Although, again, it's non-constructive, because maybe my filter is such that I don't have a dictator there. Okay, so now comes the application to machine learning. So this is for robust classification. This is a paper that we had in ICML 2023. So what is the story here? So you have this, in many different setups, we talk about a level of robustness. Say you have you want the adversarial robust classification. You want classifications that an adversary cannot distract it, or strategic classification, in which you do a classification, but the elements can strategically fake their feature vector and look differently, and you still want to not miss the classification. Or classification with improving agents, that the agents say, I have a classification, who will get to university and who will not. In the strategic classification, someone can maybe fake their marks. In the improving agents, he will learn very hard and then he will be qualified for. In all of those situations, what you want to show is that there is a level of robustness, and you want the classifier to be robust to that level. So now we address a situation in which we have a linear hierarchy of robustness requirements. So you more and more robust, you have a linear hierarchy of robustness requirements. Say perturbation sets that are balls of larger and larger radius, the robustness you want to be protected against. And assume that you have a data distribution that's realizable by a class H, in the sense that for every finite sample and any level of robustness, I have in H a classifier that is so robust for the sample, that have zero robustness loss in this sample. So again, I mean, in many cases of robust classification, you assume that the perturbations are fixed, but assume that you don't know what is the possible perturbations of the user. So you have a hierarchy of perturbations that you want to be robust against. And assume that you have a class and such that for every sample, you can get a classifier which is robust to any level. And now the question is, we wish to define an ERM learner that will be robust on every level. So you see what the problem is? You see, I mean, maybe I should explain it. I have a sample, and I want to be robust for this level of perturbation set. So I will find a classifier that doesn't intersect them. And maybe I also want to be robust to a different level. So I have an HR that is robust to level R, and I have an HR prime robust to level R prime. And now I have a sample, and I want to have a maximal robust classifier. Yes?
But if you require this to hold for any sample at any level of robustness, you can take the radius large enough so that
yeah, but I'm not saying, I'm not saying that my levels of robustness are balls. I'm saying that you have an abstract notion of robustness. Yeah, you're right. With the balls, if I want you to be robust for any radius of a ball.
So the example is not actually an example. Say perturbation sets are balls at any radius is actually not an example.
Right, it's not a good example. But we have an abstract notion of robustness, and you have some hierarchy of robustness. Yes, right. And the problem is that for each level of robustness, I can have a classifier, but I don't know how these classifiers behave outside the sample. Maybe those classifiers, although on the sample, they all classify the sample correctly and are more and more robust, maybe they have contradictory behaviors outside the sample. Because there is the robustness on the sample doesn't tell me how they behave outside. So we still want to get a maximum robust ERM learner. I'll see a sample, I will adjust myself to the sample in a maximal robust way, but I need a classifier in the class. I want to know how it is going to behave outside the sample. Can I fix this behavior outside the sample? And for that, we use happily ultrafilters. So, okay, so we have here a notion of the order over the robustness level. So R is the set of robustness level. So we have this order of robustness, and we assume that if you're robust to a higher level, you're also robust to lower levels. And we want to handle, there is no maximal robustness, it's just a linear order. And you want to handle maximally ERM robust classifier. How are we going to do it? So we consider, we have this ordering of robustness levels. We consider the filter of final segments. So every set that contains a final segment is a member of my filter. And now I extend it. I assume that I have a sample that is robustly realizable for H, by H. And so for every level R, I will pick some classifier of the sample, of level R robustness. Now I have to say, so I have here a collection of classifiers. Each of them is more robust, but they behave, I don't have any control how they behave outside the sample. So now I need to define the behavior outside the sample. So I will define H star of X outside the sample by the following trick. I will extend my final filter to an ultrafilter. And now assume that my predictions are just 0, 1. So now I have to define what is H star of X. I have a point X, I want to know what is H star of X. So for every either value 1 or value 0, I will look at the set of all R's such that H R of X equals this value. So since if I fix X, and I look at the set of R's that give me label 1 and the set of R's that give me label 0 for this H, there are two complementary subsets of my set capital R. So one of them is in the ultrafilter. And that is how I will decide how to label the point X here. It's kind of a majority vote. I have here all kind of HR classifiers. I want to decide what to do outside the sample. I'll take a majority vote. But since it's an infinite set for the majority vote, I need an ultrafilter. So the ultrafilter will decide how I behave outside the sample. And now I want to claim that this is an ERM classifier, that is, this H star of S will always will be robust on S for every level of robustness. That's pretty obvious. But I do have a problem. And the problem is this new H star that I defined may not be a member of the class. So maybe I started with a class of finite VC dimension, but it's not ERM because I'm picking a classifier outside the class. So the problem is that I now need to extend my class to include all those limit classifiers. And the question is, what will happen to the VC dimension when I go to the new class? Maybe it will blow up because I add lots of classifiers. So now we have this claim that for every H robust realizable sample S, we look at the classifier H star. It has 0 robust error on the classifier. But the main thing is that this H star, I take H and I add all the limit classifiers. I add all these H star. First of all, it is robust. Now I'm robustly realizable, but now I am outputting members of this H star. The question is, what is the VC dimension of H star? And now what I'm claiming is that the VC dimension of H star is the same as the VC dimension of H. By adding all those limit classifiers, that may be uncountably many of them, because I don't have any control. I did not increase the VC dimension of H. So it was learnable before. I can go to this class H star and use ERM over H star and get all those limit classifiers. And the trick is that assume, I want to show you that the VC dimension of H star is not larger than the VC dimension of the original H. So assume that I have here a set that I shatter with H star, with the big set. So what does it mean that I shatter it? It means that for every 0, 1 labeling of this shattered set, I have a member of H star that gives me this labeling. But having a member of each star that gives me this labeling means that for every I in the set, H star gives me on Xi the level Bi, which means that the set of all levels on which I get level Bi is in the ultrafilter. And the ultrafilter is closed under finite intersections. So the set of all functions that give me those behaviors is a member of the ultrafilter. It's the intersection of the big sets that give me the value on each Xi. It's a member of the ultrafilter, so it's not empty. It's not empty means that I have an old H there, because the ultrafilter doesn't contain the empty set. So there is an old H that gives me all of those values. So this set is shattered by the original class H. So here we fully use the whole power of ultrafilters. First, we use the decisiveness so that it will give me a value for every point, because I have the two sets, those that give me value 0, those that give me value 1. One of them will be in the ultrafilter. Then I use the finite intersection in order to show you that if I shatter a set, then the values on every set is a big set. So the intersection of all of them is a big set. I use the fact that big sets are not empty. Then I have a function for my original H that does this 0, 1 behavior. Therefore, the set is also shattered is already by the original H. So yeah, so we prove that it does not increase the VC dimension. So this is in that ICML 23 paper with Tosca and Ruth. And now I came to the most interesting story maybe, but I'm almost out of time. So I don't know how to handle it. I mean, yeah. I mean, you remember I told you before about this Emacs learning, and let me take 5 minutes, or how much? I'll take 5 minutes just to tell you the stories, right? So the Emacs learning, we said, is the following problem. You are given H is a collection of subsets of my fixed X, and I have P over X unknown, and I get a sample S that is coming from P of some size M, and I want to come up with A of S that will be a subset of my class, but will have as high as possible probability of being hit by the probability P. And this is a real problem, because when we learn uniform convergence, tell you can estimate from the sample the weight of every member of H, but that's an overkill. We don't want to estimate every set. We just want to find the best set. So this Emacs learning is a very natural relaxation of uniform convergence. And it was already, realized by Vapnik. Vapnik called it the general statistical problem. And, right, so you can think of it as David just showed me before. If you have here the members of my domain, and here I have my hypothesis, and here I have the loss of hypothesis H on the point X. So this is a point X, and this is hypothesis H, and I have an unknown distribution. I want to find which of them has, this is the loss with respect to P of H on X. I want to find which H has the maximal loss. I don't have to estimate all the losses. I just want to find the H with the minimal loss. It doesn't matter, minimal, maximum. I want to find the extreme guy. I want to solve this problem and how difficult this problem is. And is there a dimension for this problem? So, so with this very smart co-authors, Shai and Amir and Rubes, and so there is a sample compression game here. As usual in many areas, sample compression is equivalent to learnability, and here we have a sample compression game. And what is a sample compression game is that Alice get a sample x1 up to xm, and there is a Bob, and Alice has to transfer, so this is sample S, Alice has to transfer to Bob only a few points, a finite number, a bounded number of points, and Bob, of course, cannot reconstruct the set S. But what Bob has to do is to find some H in H such that H is a superset of S. So this is the game that we are playing. In usual sample compression, you want to find a small subsample from which you can recover all the labels. But here I don't ask you to recover all the labels. I just want to be able to get a superset of S. So it turns out that this game is equivalent to the Emacs learnability. And this is a cute game. I mean, it really depends just on the size of the domain set. If we are playing on the natural numbers, then if Alice gives me these points, the question is, what will be the scheme between Alice and Bob such that Alice just passes few points and Bob can recover? So I look at the set H, X finite is the collection of all A subset of X, such that A is finite. Say we are playing, Bob and Alice are playing in the game in the collection of finite sets. So over the natural numbers, it's very clear. What will Alice pass to Bob? What will be the strategy? Anybody still with me? The max. Alice will pass the max, and Bob will give you the initial segment. It's still a finite set. But so you can play it over the natural numbers. But can you play it over the real numbers? That becomes tricky. So we want to talk about this collection of all finite sets over the real numbers. Now, Alice gets a collection of finite sets of the real numbers and pass to Bob only a bounded number of points, and Bob has to not just get a superset, but get a finite superset. It has to be a member of H. How can Bob get a finite superset? So now comes the well orderings, and we say, assume that the level, the size of R is just Aleph1. So we can do this well ordering such that every initial segment is countable. So now, and this is the well ordering of the unit interval. Every initial segment is countable. So now Alice gets a countable finite set. So Alice, look at the top guy and look at this initial segment. Will this be enough for Bob? It will not, because this could be infinite. But this is just countable. So since this is just countable, I can have a mapping from 1-to-1 onto from the natural numbers. So these points of the sample, once I know what is the top, I can find a mapping to the natural numbers. And now I can see the sample here and pick the top the top element here and say, just take all the things that are images of this finite set. That will be a superset. So if the reals are Aleph1, continuum hypothesis, we can play this game with just 2 points. And we show that if the reals are Aleph n, you can play this game if and only if you can play this game with n+1 points. And the conclusion is that if the reals are below Aleph omega, this is learnable. If the reals are above Aleph omega, it's not learnable. So learnability is equivalent to the question of whether the reals are above or below Aleph omega, independent of set theory. Everybody is happy. That's the story here. Thank you.